Hi, my name is Gabriel Huang, and I will tell you about repurposing pre-trained models for robust out-of-domain few-shot learning. This is a joint work with Namyoung, Huidong, and my advisor Simon, and this work was done while Namyoung and Huidong were visiting researchers at Site AI Lab in Montreal. There are many challenges with using deep learning in the real world. For instance, we might not always have enough task-specific data, so we consider the few-shot setting. We might need more out-of-distribution generalization, and we might have limited access to the meta-training dataset due to security, privacy, intellectual property, or legal reasons. We might also just have limited training resources, especially on a mobile device. Meta-training might be too costly. So this is why we consider the new setting of repurposing pre-trained mammal checkpoints to solve new few-shot tasks without the possibility of retraining on the meta-training set. Under those constraints, can we get the best generalization performance, and can we improve over the default mammal steps? This is our experimental setup. We start with a pre-trained mammal checkpoint and we don't have the possibility to see the meta-training set. Then we will do meta-testing, so we could either use the usual mammal or we could apply our method. So we will consider mini-MinchNet for same domain benchmarks and CUP, VGG flowers, and traffic signs for the cross-domain setting. As usual, we fine-tune on the support set and then we evaluate on the query set. So the question is, how can we improve the fine-tuning step? Our method consists of the following components: adversarial training for data augmentation, deep ensembles for uncertainty estimation, so estimating the variance, and then we propose two tweaks: uncertainty-based step size adaptation and uncertainty-based fast gradient sign method based on the following principles. Principle number one, we want to use lower step sizes for model parameters with higher estimated variance. Principle number two, we want to use adversarial examples with higher adversarial perturbation on input components with higher variance over the input gradient. We will also consider the following losses. This is the usual cross-entropy loss, and we will combine it with the adversarial loss. So this is just a cross-entropy loss over adversarial examples generated using the fast gradient sign method. So we start from some noise, and then we will scale it using the sign of the gradient. Let's walk through our method. We start from the mammal checkpoint and we perturb the checkpoint using some Gaussian noise to generate the ensemble. Then we will fine-tune the ensemble models on the support set using a combination of cross-entropy and adversarial loss. Then we will apply uncertainty-based step size adaptation and we will scale the parameter step sizes inversely proportional to the variance. We will also apply uncertainty-based fast gradient sign method and scale adversarial perturbations proportionally to the input gradient uncertainty. Finally, we restart from the initial checkpoint and we'll take gradient steps using a combination of cross-entropy and adversarial loss on a combination of the support set and the augmented support set. So those are a lot of tweaks, and so we did a lot of experiments to know which things are useful and which things are not. We consider the top one metric, which is just the absolute performance after tuning for the best step size. And we also consider top 40% and top all metrics, which are averages of the performance over a range of step sizes. And this is to see how robust we are to the choice of step size. We consider 5-way 5-shot classification. X-axis is the step size, Y-axis is the accuracy. And you can see that in orange, our method is more robust to the choice of step size and has slightly better top one performance. Now in more details, we have comparable or better absolute performance on same domain benchmarks. Here are some numbers on mini-MinchNet. On cross-domain benchmarks, our method also improves the absolute performance. So here are some results on birds, flowers, signs, and average of the accuracies. In the 5-shot setting especially, our method significantly improves on the robustness to the choice of step size on cross-domain benchmarks. And our method gives comparable or improved robustness to the choice of step size on the same domain and cross-domain benchmarks. So we have performed some further ablation study, and we can see that the most useful component is probably the adversarial training. We have applied our method on overfitted checkpoints and seen that it works as well. Finally, we have frozen the most uncertain layers, and those were the batch norm scaling parameters, and it helps as well. To conclude, we have considered the new setting of repurposing mammal checkpoints for out-of-domain few-shot learning. Our method uses deep ensembles to estimate parameter and input gradient uncertainties and builds upon mammal through the addition of adaptive step sizes and adversarial training. The results motivate using adversarial learning as data augmentation for improving few-shot generalization, and in the future we'll apply our method to related settings such as domain adaptation and transfer learning. Thanks a lot for your attention. Wish you a wonderful conference.